Starting the recording. Well, good morning, everybody, or at least at this moment, two everybody's. Um, my apologies to the group. For some reason, WebEx seems to have deleted the link, so I know that probably has caused some problems. I'm going to look into what's going on with this because this is not the first time WebEx has done this. And hopefully this recording will help those who missed it. What I want to do for today is we're going to talk about brain waves. This is kind of a setup for Thursday. We will again do hopefully a WebEx, or if this gets too annoying, I'll look into seeing if we can do Zoom or something else. But we'll meet online on Thursday at our usual class time. And my intention is to kind of walk you through in MATLAB how we can do a EEG processing. And if you're interested in it, you can download. There is a really nice kind of MATLAB toolbox that's free, put out by University of California, San Diego, called EEG Lab. So you can download EEG Lab, and it's got everything you need to process EEGs, also MEGs, and some other ones. And it has interfaces for doing ICA and all the other stuff that I've been making videos on. And you can kind of pull parameters and you can choose different ones, fast ICA, like iDemo, things of that sort. So you can use all that experience you've got on it to be able to tune to get a good answer on your independent component analysis to figure out the regions of the brain that you're doing things on. Um, so we'll do all that on Thursday, kind of walk through and look at it and how do you process it so you're familiar with at least the basic processings of doing this. And so in order to do that, I want to talk about kind of what you would see in the waveforms. And there are bands of brain waves that are out there. Um, for instance, we'll talk today about delta and theta, alpha, beta, and gamma waves. So those are kind of the main groupings of brain waves, and they have different functions within. We'll take a look briefly at what a sleeping characteristic is, and then I've taken some measurements on myself using just a single measurement EEG from MindWave that I have that allows you to measure these. So I'll show you a couple different ones I've pre-recorded of me doing some activities, sitting or, singing along with a sad song, watching a video, things of this sort. And then I'll kind of hook up and show you how it works for measuring just individual ones. So that's kind of the plan for today. That will probably not take our full hour and 15 minutes. My plan was then to use the rest of the time for kind of Q&A on either Pulse Ox or on the project. So that's the plan. Let me see if I can share my screen here. All right, so hopefully everybody can see right now Keynote. Is that correct?
Correct.
Awesome. All right. So let me break down. I found some nice pictures on the web, and one of the things that I actually think is kind of important to understand when we're talking about these brainwave ranges that you'll see in here, you'll notice there is no agreement on the exact frequency ranges for the brainwaves. The general areas are absolutely agreed on. The exact boundary is not, and part of that is that it's not quite that crisp of a thing. There are some very related patterns that go on, but it's not quite as simple as just saying, hey, if it's at this frequency, it's exactly this. So there's a range of things that are associated with these frequencies, though. But let's kind of walk through them. The first one that we hit kind of not necessarily time-wise development, but starting on a frequency range. Usually the range of it's about 1.5 to 4 hertz is what's called delta waves. Now, I've seen some people push this, like the furthest one I've seen I put up here that gets down to, they claim 0.2 to 3 hertz on the low end. Um, Usually people claiming below about 1.5 hertz, maybe even 0.5 hertz, are usually claiming some type of a deep meditative trance type of a thing. Um, Delta waves are associated with very deep sleep. You don't usually see delta wave activity unless somebody is sleeping. Um, you might occasionally see a spike that's very, very low frequency, but on an awake person, but generally you're not going to see um, any activity other. But delta waves absolutely kick up. Once your eyes close, you'll start to see some delta wave activity kick in. And it will increase as you get more into what's called deep sleep. And once you're into deep sleep, when you go to REM sleep, it'll kind of move back up to theta waves and then back. And so your sleep activities are really kind of varying between delta waves and theta waves. Next slide, I'll talk a little bit more about some of the sleep activities because there's some interesting things you'll see inside of the brainwave measurements that go on that are characteristic in sleep and can kind of be insightful in understanding what's happening. Plus, they also help you understand why we care about location where things are going on. All right. So delta waves, when you hear delta waves, think, basic unconsciousness for most of the part. Um, and Anywhere up to 4 hertz, I believe, is actually the clinical definition. Um, but they will often split this into two ranges. So, below 2 hertz is used for the deepest deep sleeps. So there's when you get into them, there's kind of stages we'll talk about in the next one. When you get to the deeper stages, 3 or 4, modern ones just cut it to 3. Older ones will have both stages 3 and 4. And the difference between 3 and 4 is more this presence of 2 hertz and below delta waves. So as you get deeper and deeper sleep, basically you get lower and lower delta waves that are going on. These are associated with a lot of restfulness. So delta waves, restfulness, unconsciousness. Um, Theta waves are associated with that, what you will call a drowsy state. So when you start getting sleepy, you're kind of, in and out type of a thing. When you're starting to drift off to sleep, when you lay your head down on a pillow, things of this sort, and, you're kind of drifting through the day. Um, you know, these are classic kind of theta wave areas. And that's where you'll see most of the stuff. However, theta waves are also associated, even though everybody just talks about with the sleep context, it's also associated with very chill emotions. When you're just really kind of super calm. It can also be associated with uh, like very heartfelt stuff that doesn't necessarily get you really riled up, but just kind of more that kind of quiet emotion. When somebody gets very emotional, but in a quiet sense, you'll often see a peak in theta activity. Um, I only see this type of discussion in a lot of the literature, but it's very common in most of the literature to talk about theta wave activity as associated with some of these kind of deep, quieter emotions that go on. So a little bit later on in here, I have some examples where I'm listening to kind of a sad song type of a thing, and you'll see there's a theta wave spike in my head when that goes on. Um, it's a type of thing when you see tear-jerker movies, you'll tend to get more theta wave activity too that happens. So a lot of these type of things are also theta wave activity, and you won't. It's not often listed because on the kind of cursory stuff, it's hard for a lot of people to necessarily connect together the ideas of drowsy sleep and kind of heartfelt emotions in some sense. Anyway, alpha brain waves are kind of they're also associated with people who are very relaxed. Um, so it's if you're just like imagine you've had a long day and you've been, doing a lot of work and thinking and whatever else, and you just sit down in a chair and you're like, right? You're going to start shifting from beta waves, which are kind of your active thinking zone, into alpha waves. And so they're sometimes called the chill brain waves too, because you're awake, um, but you're kind of more like, in that really relaxed state. And you know, as you move from activity towards sleepiness, you'll tend to see the brain move towards alpha waves. So sometimes people call it drowsy, but that's actually not a really good statement. So, and the reason why I say it is people who are drowsy do have alpha waves, but alpha waves also will underlie as kind of like almost a regular beat inside of a very active brain, also. And so they also seem to be kind of a pulse timer for an active thinking person. They kind of function in this kind of more timing of a behavior pattern. So, um, it's not only in those, it's kind of underlying all of your thinking. So when you're awake, you do tend to have alpha waves kick in, and they'll be higher or lower, and they tend to transition you either from sleep or into awake, or kind of keep you in awake. um, so just like delta waves, I said, were below 4 hertz. Theta waves are usually in that range, 4 to 8 hertz, maybe 9, but 4 to 8 is pretty good category range for them. You can see that on one of the groups they mentioned 3 to 8. Like I said, that's a rare number. 4 is probably the most widely accepted branch or breakpoint between delta and theta. Um, and then when you go to alpha, it's often listed as 9, but that's just because they're kind of walking by integers. So anything above 8, and it will vary in range. I've seen from 12 on the low end, 13 is pretty typical. I've seen 15 and 17 mentioned by some people as the alpha wave barriers, but 9 to 13 is probably the best overall um, consistent range you'll see for those alpha waves, which again, that's kind of the underlying beat of awakeness, but it also kind of handles your transition to drowsiness and your relaxation. Usually that drowsy relaxation is when the alpha waves are dominating. So if you don't have a lot of beta or gamma activity going on, then you've probably just gone from a very active state, and you're kind of moving down. And you'll see as the person relaxes more, they'll start at what's called high alpha, the higher frequency ranges of the alpha waves, and it'll start shifting down, 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 down. So if you watch that transition as the frequencies kind of shift down, you're moving more towards the theta wave. You're kind of, that's more characteristic of drowsy. So there's a little bit of activity going on. But if you really see alpha dominating, then you're in that, most likely in that kind of chill, um, less, active, kind of lethargic or whatever you want to call it state. Um, so that's alpha waves. Beta waves are kind of your, when they dominate, that's the awake, I'm alert, I'm doing stuff. Um, your typical thinking on a problem, not intense thinking though. But if you're working on something, so you're active, and the higher the frequency, the more kind of intense the thoughts are going on. So amplitude is not a measure of brain activity. This really throws a lot of people off. But your sleeping ones are going to be much higher waveforms in amplitude than your actual conscious one. So the amplitude will drop as you think harder, but the frequency will increase. So don't think amplitude has anything to do with the intensity of your thoughts, And this is kind of like a cartoony idea, right? It's really concentrated, so the voltage and everything kicks up. Not true. The frequency kicks up, but the voltage actually drops. Um, so you're not generating a stronger electromagnetic wave. You're just actually pushing it into a higher frequency range. So those beta waves, and they'll go anywhere, usually, let's say like 13 to 30 is a pretty typical range. They used to be all the way up to 40, but usually when you see somebody who lists 40 or even 45, sometimes 37, when they list these high numbers, as the upper ranges for the beta waves. That's because gamma waves were added later, and those kind of upper frequencies got allocated to gamma waves. So they kind of split the beta off and then went higher frequency with them. So the essentially take that kind of 13 to 30. It's one of the two I put up here for you shows 12 to 27. If you notice, you'll see that tendency. I think the one on the left does this a little bit better. You can see the slower wavelengths, but they're higher amplitude. And as the frequency goes up, more spiky noise, you tend to get, you know, the actual amplitude drops as the frequency increases, but you're getting more activity. So beta waves is kind of like your typical I'm on task, I'm doing my job type of stuff. Typical brain activity. When you go into very intense thinking areas, you're trying to solve a new problem. You're trying to learn something. This is sometimes called the education area. You're deeply and intensely thinking on a problem. That's when you move into what's called gamma waves. So the gamma brain waves are usually 30 and above. Um, Most of that activity is going to be between 30 to 40, maybe 45. It's very rare to get above 45. There are some cases with some very intense problems. We've seen people's brain waves kick up above. But for any type of a normal activity that you would experience, 45 is probably an upper limit to what most people get to. And so that's in there. There's most of the time with most of my brain wave activities that I'll show you, you'll see I kind of put 40 as the upper limit. There's one of them where I had to actually expand it to 45 because there was significant stuff out there. Usually after somewhere that 40 to maybe 50 hertz, it drops off pretty rapidly on the curve, the amplitude when you take a Fourier transform. And so you can pretty easily tell that's where the end is. There probably are some minor beats that are going on there that are real things being generated, but a lot of it's just noise also in the system. So usually people will put some type of a filter, and 50 is often a good break frequency, sometimes 40, depending on what type of activity they're doing. Sometimes people set that 100 just in case there is some stray activity up there. They don't want to wipe it out with a filter. All right, so that gives you kind of the general groupings of brain waves that are out there. Let's take a look. Sleep is a good pattern because you can see a lot of activity that's in here. So if you look on the very top one, I like this one for a lot of stuff. It doesn't do a great job identifying everything, but it actually has a lot of interesting activity that's in here. So you'll see in here the top one, there's a lot of alpha waves going on. This is kind of, you're getting chill, you're getting ready for bed, it's been a busy day, you're kind of feeling it, you're processing the things for the day, but you're kind of relaxed and, oh, what do I have to do tomorrow? But you're kind of getting, kind of calm and ready for bed. So that's what you're going to see here with this alpha wave type thing. The awake but relaxed just before bed, kind of getting ready for bed activity. You'll see right here stage 1 sleep that's going on. Notice that there's really frequency wise, it's kind of similar that's on. But what you'll notice is there'll be some kind of some sparks in between here, right? Where there's kind of slower wave stuff. And that's often what you'll see is you'll start to see a few theta waves kick in every now and then. These kind of every now and then some slower waves that are coming in, and then a little burst of activity. So when you're first dropping off to sleep, at this kind of stage 1 sleep, this is very characteristic. Your brain's getting a little quieter and it's starting to move into this on-off rhythm. And what happens when you see these kind of higher bursts, and you see them more intensely right here, there's still a lot of alpha waves going on. You're alert to your environment. So the alpha waves are also associated with your senses detecting the environment around you. So you're aware of what's going on. And so when you're having these ones, you're falling off, you can still, that's how you can kind of sometimes you almost hear a little bit more and you're kind of scanning it. This first one, you're not really doing a lot of thinking, right? It's more that you're kind of your brain is checking, hey, is the environment okay, right? Um, you're kind of hearing around the area. Is somebody opening the door? Is somebody moving into my space? Things of that sort. Your body's kind of checking the area out because it's about to go to sleep, where it's not going to be as alert. So this is kind of it's scan the environment zone that's happening at this first kind of stage. So you're getting more relaxed, and it's doing kind of a sensory read around of everything. When you get into this second stage of sleep, you are really asleep. So you're very drowsy in sleep one, and your eyes are probably closed, but you're not unconscious, right? There are some thoughts, and there are this kind of sensory scanning that's going on. When you get into stage two, you're asleep, right? I mean, this is like, you are asleep technically with stage one too, but you can wake somebody. They're a little bit drowsy, but it's kind of more like the annoyed thing. And it doesn't take too much, like a light noise or something like that will wake you up in stage one. Stage two, it's harder to wake up. And when the person wakes up, they're not really completely with it usually when they first get up. There are two characteristics. Besides, you'll notice that there are some of these bigger theta waves that have kicked in pretty strongly. And there are some delta waves that are coming in here in between, but there are two ones. They've labeled the sleep spindle here. And this kind of higher spike, it's actually the largest spike you'll see anywhere, is called a K complex. And they do appear in a few different areas. Um, they're related. Um, a spindle is a burst of alpha activity. So if you've ever woken up in the middle of the night and you're like, something doesn't feel right, that's the reaction of your body to a spindle. So the spindle comes in, and even when you're sleeping, it kind of does a quick probe of your senses to say, everything's still okay. And it'll kind of do this polling subconsciously to see if it hears a noise or whatever else. If it detects something it feels is out of the ordinary, then you will go into a wake up phase to kind of let you deal with it. If it is considered a no problem situation, it'll be followed pretty shortly thereafter by a K complex. K complex is a very large delta wave basically that comes in and says, go back to sleep, right? um, now, K complexes will appear also at other times without a sleep spindle because they're also used as one of those rhythms to keep you asleep. So K complexes will serve two purposes. The spindles do also. One of them, though, for the K complex is to keep you asleep. The second one is associated with memory. So it allows you to kind of to collect all the memories together. Part of the function of sleep is also for you to kind of sort through your memories and kind of collect them together. It's like your brain kind of cleaning through itself and deciding what needs to stay and what doesn't. And the K complexes are also associated with triggering those. Um, the sleep spindles are associated with that kind of quick scan of the environment, but they're also associated with triggering the kind of collection of memories also. So they do a double purpose. The sleep spindles actually originate in the thalamus area of your brain. So right next to the cortex. So this is why we know that they're dealing somewhat with the senses when they're reading through them, because um, they're kind of the thalamus does a bunch of things, but one of them is that it kind of watches over processing things from the cortex into your main brain. And so in that area, these spindles that are coming in are used kind of to kind of watch that activity flow to say, hey, what's going on here? Um, and if anything's out of its kind of normal because it watches this all the time, then it goes, okay, boom, wake up. Um, Otherwise, it will kind of trigger to the rest of the brain, right? Everything watches, and the rest of the brain says, okay, no problems, go back to sleep. Hence the K complex delta wave. Um, but both of these are also used in a function of kind of collecting your memories together, because a lot of those are processed in this sensory way. So anyway, that at that second stage of sleep, you'll see characteristically it's mostly delta and theta waves together with these kind of burst of alpha waves called spindles, and then every now and then these really big delta wave spikes called K complexes that are in, and you can see it's like significant. It's um, identified as the largest single spike activity the brain ever produces is these K complexes. Stage 3 sleep, you'll sometimes also see these the first stages here, 1, 2, and 3 will sometimes have an N in front of them. That's for NREM, right? REM is rapid eye movement. So stage 3 and stage 4, I've mentioned this before. Right now they're actually, for most studies, 3 and 4 are connected together and really joined. Only difference between 3 and 4, like I said, is you'll see the delta waves get bigger and slower. So when they drop below 2 hertz, that was the old definition of stage 4. Sometimes people will just merge them together, like I said, nowadays, and say when below 2 hertz starts to appear, you're in stage 3. When it dominates, your stage 4. So sometimes people just say, hey, we just need stage 3 once the below 2 hertz waves appear. This is actually usually about a big maybe 20% of your sleep. Stage 2 is about 50% of your sleep time. Yet maybe 10% stage 1, the rest is REM sleep. Stage 3 is where the biggest kind of relaxation in your brain happens. This is where the rejuvenation and everything else goes on. So that kind of very slow, your brain is just totally relaxed. It's not doing anything. It's just kind of totally resting and recuperating. Um, that's what stage 3 is there for. You see that it's really just dominated by those delta waves. You pretty much do not see any theta waves, maybe a tiny bit of activity. The old def for stage 4 was not just that 2 appeared, but that basically you didn't see thetas anymore. So when the 2 hertz and below dominates and there's no theta, that was stage 4. But we found out functionally they pretty much seem to do the same thing. So as long as you're getting a pretty much this area where the theta waves have kind of gone away and you're really just dealing with these very slow delta waves, that's your deep regenerative sleep. Um, and then every now and then out of this, your body will pick up again. You can see another K complex in here associated with keeping you awake keeping you asleep, because we're going to move into a theta wave period. That's what REM, rapid eye movement phase, goes on. You can see kind of the theta waves, and then you can see the eye movements, which are bigger, right? And your eyes in this really they'll kind of, I don't know if it's easy to, when you see it, the person's eyes will be closed and you'll see them move kind of rapidly around, right? That type of, eye moving rapidly around, but underneath the eyelid is characteristic of REM sleep. So you'll see these type of eye movement spikes that come in, but it'll be basically dominated with theta waves and some K complexes that kind of keep you in sleep, because you don't want to go from theta and then move up to alpha and wake up. So those K complexes are needed to handle it. But this is when you dream. So those theta waves are associated with dreaming. And it's kind of, this is why I say a lot of your emotions are kind of at theta wave level. And it's not that all of them are, but there really is a lot of this. This is when you're thinking back over. Um, and this is why your dreams often show what you're feeling about a situation, because that's what's going to get brought up. And it's the brain function that's processing, you know, what was kind of going on for the day. And that's why most dreams will actually have a meaning that's related to kind of what you're going through. That's, you see the classic stuff like people have dreams of falling, and that's usually, associated with people who feel their life is out of control. Doesn't mean it always does, but there is a lot of this correlation, because your brain is going to reinterpret your emotions carrying in these theta waves, and kind of have the dream activity where you're processing through what's going on with this. And it's trying to figure out, what do I do about this? So very often you'll deal much more at an emotional level inside your dreams, and this is why. Bunch of stuff, 2 slides. Any questions so far?
None here.
Awesome. All right, I'm
I
gonna
have
go
a
on.
question. How
Question? Yeah.
were these recorded, or are these just relative examples?
So these are relative examples. I took this from a sleep study thing where they were talking on them, but you can find a bunch of these that are out there. I'm going to show you actual recordings starting right now that were done on me. But you know, I'm not really in a spot to be able to do a sleep study on myself, particularly not when REM sleep, to go through all these stages of the sleep area. You'd really have to go and do a kind of longer, you need at least a 3-hour chunk to do a decent one, because that's a typical sleep cycle in a person, is blocks of 3 hours that you'll go through these. And that'll be broken down into subsections, but one kind of full um, cycle of all the things is usually somewhere around 3 hours for most people. So these ones are just kind of characteristic. They're kind of fudged, and I picked ones that had the features on them I wanted to show to you, just to gear them. But this is an actual, so this is a frequency. I put them in the frequency domain because I think it's easier to see than the time domain. But this right here that's actually me, and it was measured on this. So the ones you're about to get here, you're going to see are characteristics of these. And I've just plotted these. This is amplitude, and this is frequency on the bottom axis. So you can just kind of see some characteristics. And I didn't do full sleeping, but I tried to get some things like here I did where I'm just relaxing. So this I took at the end of the day, and I have a comfy little recliner chair, and I reclined the chair back and just kind of, breathe deep and close my eyes and just, relaxed. And you can see as I was sitting there relaxing, I've got a strong spike right in the theta wave area, right? So, you can definitely tell I'm feeling pretty chill. There's a little bit of alpha waves, a little bit of beta on here because I'm kind of moving out from a time when I was thinking and my brain was kind of like very actively moving, and it starts moving towards this spike, right? So I was kind of, um, you know, it's just kind of a chill, relaxed time. And sometimes I'd kind of open my eyes because I was sitting there. My son was watching a movie, and so he and I would talk a little bit while I was measuring this too. So, but it was a very relaxed time to me. And so there's very little activity going on but the theta waves that's in here. So you can kind of get an idea of what it looks like. And this is why I'm saying you won't have like no here, you've got definitely some alpha activity going on, a little bit of beta. This is probably, spikes that were occurring from when, my son would mention something and I'd talk to him a little bit. But the biggest dominator of this is the theta wave pulse that's coming in here. Does that make sense? Yes and yes. So sorry if, since I'm on the keynote, I can't also see any comments that's typed. I can see one or the other. So at the moment, I'm just on this one. So I also tried to do a thing where I was sitting and thinking. So after I kind of did that one for a little bit, I took some measurements. They were all very similar. So I really just showed one of them. So I tried doing one here where I was thinking on something that was very interesting to me. So where I was kind of very mentally active, but I'm totally relaxed and on sitting in the same chair. This is actually maybe 5-10 minutes after the previous one because I just collected a whole bunch of these. So this is right after a very relaxed period, and so then I started going, maybe I'll see if I can get a lot of activity going on. So I gave myself kind of one of those challenging, hard problems that are sometimes fun to think about. So you can still see the theta waves were starting off as I was starting to think of it. Um, there was still a little bit of a pulse there, but you'll notice this huge section of gamma that's in here, right? So I'm at 30 hertz and above. I actually had to carry for this spike here, I had to carry out to almost 45. So you can see my brain is like on high activity level at this moment here. So that problem instantly shot it up. You'll see a little bit of beta wave, but remember I said you'll also kind of have this underbeat of alpha all the time. So you can see this kind of characteristic beat right there at the upper end of high alpha. So we often will split alpha into low alpha and high alpha. So remember, alpha goes from about 8 to 13, maybe 14. As this pulse moves towards the upper end, it's kind of the underlying brain activity beat or pattern of a very active brain. As it shifts down, it's kind of moving to a more relaxed chill zone. And you can see I'm up on the high alphas, and I've got this huge section of gamma going on. So that's a very, very active thought pattern that I'm dealing with. Some other ones that go in here. I thought, okay, well, an interesting problem challenging me that I was trying to think on and solve a problem kicked up those. What if I watch something that I find to be an interesting video? Now, in this case, the interesting video, I like trivia. I really can't tell you why, but it's fun to me. So I like a lot of particularly like movie trivia, what kind of happens to them. Um, so I enjoy watching like the what culture videos and stuff, and what happened behind the scenes to cause certain things. So I thought, well, those are kind of fun, and I'm usually thinking about them. Um, I wonder how active I'm really, involved in these. And so I put one of these on and I enjoyed the content and everything, but you'll notice that my gamma activity just dropped through the toity bowl, right? It's really low. I mean, there is some activity. You'll see a couple spikes here that's going on, but this is low beta, right? That zone 13 through say 30 is beta. So, I'm below 20. I'm in the lower part of it. So I've got some beta activity going on. So you can tell I'm thinking about it. Um, but it's not huge. Um, there's a little bit of high beta, but my gamma is just like whoosh, dropping off, and you can kind of see the general trend going down. Um, so there is some kind of activity there. There's some little bit of low alpha going on. You can see these two spikes here are both in low alpha. Um, I am emotionally interested in what's going on. So you do see a lot of this theta area. And, so that activity is happening, but I'm also am becoming a little bit not as focused and drowsy. So if you've ever even been watching a video you were interested in and you start feeling drowsy and falling asleep, your brain is generating a lot of this theta and particularly a low theta. Um, and so that emotional one is not going to get you as much as mental activity will. So as the mental activity drops and the theta dominates, you're going to become less and less focused on the idea. And this is probably why I enjoy them, but I don't know why I enjoy them. Um, it's just kind of fun, but my brain really is kind of checking out as I am watching this, even though I'm enjoying the content of it. And I thought, well, would that change drastically if I switched to a different type of video? So I also enjoy a lot of sad songs. So I put on a sad song. And you'll notice, I mean, it almost looks like it's the same thing. So I'm going to flip back and forth. But I promise you, these are different measurements. You'll see a little subtle change between them, but there ain't much. So from watching an interesting video to watching a sad song, I kind of closed my eyes. You can see my eyes close here when I was just kind of listening to it, and I'm definitely feeling the song. There is some activity. It's a little bit higher there, but not by much. So, we really are not as plugged in when we're watching videos. So, you know, I'm sorry coronavirus has stuck this, because at this moment you're probably like, dang, he's talking. And even if you're interested, it can kind of cause you to zone out, and just mentally it has to. Um, so I kind of wanted to see one other thing. So I took that same song, and partway through, I started singing along to the song. Right? So I opened my eyes and I started singing along. You can see there's a little bit of delta because I had my eyes closed at first. I was doing my second reading. I'm like, I should actually probably try something different with this. Let me try singing along. So I kind of sang along with it, and notice what happens. Right? Now that I'm interacting with the song, boom, I've got a huge kick up. Right? Um, so, my emotions are still engaged. You can see the thetas here, um, a little bit drowsy, but look at the kick up in my alphas, including even getting to, a little bit into the higher alphas. Um, my betas are there, but I'm actually even getting a little bit of gamma, because I'm at that point, I was kind of really kind of more intensely, and I was thinking about it, and I was engaged with what was the song talking about. So it kind of made me think about it. I was contemplating, wow, what does this mean for me in my life? And so you can see these gamma spikes kind of kick up. Um, and I took two of these measurements, right? One in the middle of the song, one at the end of the song, right? And at various times, I would kind of, like when I'm singing, I'd close my eyes and sing along with it. So you can still see these delta wave things as I'm going on. But again, this looks like it's the same thing, but they really are, you know, these are, I took these in 15-second measurements. Um, and so this one was the dead minimum of a like 3-4 minute song. So it was like a, minute and a half, 2 minute zone. And this one was right before it ended. And if you look at it, it's almost identical, the pattern that's going on. So, me singing along with that same sad song, it didn't seem to matter. My brain activity, nearly identical between the two. So it does show you that while an individual spike, um, you'll see activities like spindle activities that'll be associated with it. Um, but the general overall frequency wave does, as a pattern, tend to indicate a very similar thing. So we see it here with singing on a sad song. We see it with just watching a video, even though they're different videos. Um, there is a characteristic to them. So you are less engaged on those. So that's what I do, try to every now and then ask questions of you, even in the midst of a video, is really to try to kick you more towards this zone. Because when you see this activity that's above 30 hertz, you're more likely to be actually remembering it. Anyway, those are some kind of straightforward measurements. I was then going to just kind of demo how this works, and then I'll leave it open for questions on this or other areas. Any questions so far? I'm going to stop
What
sharing.
instrument did you use to measure these?
Um, I'm sorry, I didn't quite catch that.
Sorry, if someone's mowing outside, I'm gonna go.
Uh, no worries.
What instrument did you use to measure these?
Okay, so this one is a MindWave Mobile 1. So, I got this a few years ago, actually, and typically I've actually got two of these, and I usually kind of clean them off a bit and then let people try them in class. Unfortunately, we don't, because you're not here, I can't let you try them in class. And I'm gonna kind of demo it right now. But basically, it's got a battery. Um, it measures the voltage. So if you look here, this goes on the forehead, and there's a metal clip to it. This, I don't know if this makes it easier to see. There's a metal section here, which is the electrode. That's going to go on the forehead. Um, and it measures that voltage relative to your earlobe. So there's this little clip here that clips onto your earlobe that has electrodes in it as well. And so it measures the potential of this area of your brain relative to your earlobe. since there's not a lot of brain activity going on in your earlobe, it's a good general thing for the voltage of the head. And there's not a lot of muscle activity. The only major muscle activity that kind of acts between here and here is your eye. And so that's still useful for a lot of engineering control because blinking is a big feature that can be seen. And then it's inside this kind of ear area. It does basic processing, and then it has a Bluetooth and it streams. So the basic processing, it breaks them down into those groups, the alpha, the beta, so on and so forth. And it also looks for an eye blink, since it's a muscle activity, is a really big pulse. So it's not a brain activity, it's still electrical though. So basically you'll see this big EMG pulse that comes in when your eye blinks. So eye blinks are usually pretty easy to tell. Does that make sense?
Yeah, thank you.
You're welcome. All right, let me see if I can get this fun thing to. Okay, right now I've got paired with my computer. I don't want to pair it with my computer. So I'm going to see if I can get it to unpair. Okay. So there's a little blue indicator light on here. When it blinks once, it means it's paired. When it does these double blinks, it means it's unpaired. I'm going to try to get pair up with my phone, because I've been able to do this better on my phone. Kind of sad, but the apps available on my phone for monitoring this are better than the ones on my computer. Pair up. We'll see if this works. And right now I'm just going to use their app, which is called Brainwave Visualizer. This is not the way I measured it, but it's got a nicer interface. I think it'll be easier for you to see. So at the moment, it's not going to show a lot because I haven't hooked it on my head yet. But if you look, it's got several different things. It'll show you the actual electrical wave on here, so you'll be able to watch it. And then on this circle, it's got different activities on that. So the top is delta waves and then theta waves. Yeah, so right now it's measuring, but it's measuring just, regular potentials out there. Right? So my non-person is dead. Low alpha, high alpha, low beta, high beta, low gamma, high gamma. So kind of breaking them into those areas. The low alpha would be, say, for instance, 8 through like 10 or 11, right? And then 10 or 11 through, say, 13, 14 would be high alpha. And similarly for as you're kicking in beta, right, you're going from somewhere 13, 14 up to, say, 20, and then 20 through 30 is your high beta. And then your low gamma is typically, say, 30 to 37, and then 37 through 40, 45 is your high gamma. And then occasionally there's some blink activities, but I don't think they show the blink on here. So I've got this on. I'm going to try to get this hooked up on my head here, right? So the electrode is on here, and then I hook the other one onto my earlobe. And you can now see that it's active. I'll try to get this so you can see me and it. And you'll see as I'm trying to talk to you, you can see it kind of spreads out. I'm going to kind of close my eyes and try to relax for a sec. Right. So you can see that it kind of chills down. Now I'm engaging again, and you can see the waveform kicks up a bit. The colored bars are actually the frequency ranges on them. the red is down in kind of the delta zone, and it goes up to 50 hertz, which is the kind of pink. So blue, purple, and pink are all gammas, um, and the others you're kind of scaling down. So this kind of gives you the kind of a readout on there. If I think intensely on something or like concentrate heavily, you'll see peaks come up in certain areas, and it'll move around as you focus on them. So if I look at this and I try to think heavily on a particular person or recall it, read a name, read a whatever, then my phone will kick off, of course. One disadvantage, this does not block the screen from turning off, so you do have to kind of keep interacting with it. So sorry. It takes a few secs once it turns on to start processing the data, and then hopefully it should back in here in a sec. Come on. There we go. So we can kind of see as we're here, the activities and whatever I'm doing reflects on the behavior that it's kind of reading out. So I'm engaged in talking with you, so you should see somewhere in the middle here. I should have a lot of alpha and beta stuff going on. And as I'm trying to think, okay, what do I want to talk of and what are people imagining? You'll see some gamma spikes. And once I get into something, a train of thought, the gamma spikes will spike down, and I'll kick back up more into the alpha beta as I'm kind of carrying through on a thought that my brain kind of is like, okay, next thought is this, right? And you'll see my gammas will spike when I'm thinking, okay, what's the next major area? And then it'll shift to alpha beta type waves as I'm carrying through and explaining those ideas. So you'll kind of see these patterns of explanation that happens on here. And then if I were again to just try to calm myself down, you'll see some drops usually in the activity level. The other interesting thing is if I blink a whole bunch, it should show you a lot of blinking activity that's on here. I don't know how easy it is to read this, but you should see, yeah, you can see there's, if you look on the little white line here that's coming in, that's actually giving you a measure of what my activity is. And I'm blinking now, so you should see those big pulses came through. Those are blinking. Blinking. And you see the big pulses. So that gives you an idea of what these are. The way in which I measured them was actually in a different app. So that one is their brain visualizer app. They're kind of more picturing. It's used by people to try to rest and meditate. So I also have this one, EEG ID, which has a completely horrible interface. It's really hard to see, but it's just basically white with almost unreadably tiny text because it's trying to put a bunch in. And it's got a lot of different ranges in here. Every activity that can be, it gives you your raw EEG and everything else. It's got on here a series of things. What's your recording time that you want to do? You'll see it's kind of bouncing if you can, I don't know if you can read it because it's so bright. You'll see the values are kind of moving constantly. That's actually, it's reading out the values right now. So what I did is I set for the 15-second time period, and then the record, I did all. So I just record everything that was there. I didn't put my GPS location on because I didn't care. And then there's this record button on the bottom. So I just press record button. And this is kind of me talking and teaching to you. And it's actually recording my brain waves now. What am I doing? How am I thinking about it? All that's getting recorded onto this. And then after 15 seconds, it'll pop up a little thing saying, hey, do you want to email this? So it'll have a CSV file that it will create that has every single thing that's measured. Now, in truth, it only measures one thing, the raw voltage, but it will also do frequency processing, and it'll pass out, here's your theta wave ranges as a result of its hardware Fourier transform. All right, so it's now popped up, and then I just picked Outlook and I just emailed this to myself. So that's how I kind of process these. So when you are looking at those ones, that's actually how I got them. And you'll see here when it brings it up, it names it and it gives you a CSV, and then I drag and drop it into MATLAB and process it inside MATLAB. So I'll just mail this one to myself. In case we want to see Keith teaching as an example, and away we go. So that's kind of the basics idea. Now, usually when we do an EEG measurement, we do a lot more than just one. One is sufficient if all you're trying to do is a simple brain-computer interface, and you want to measure things like, is the person restful? Is the person alert? Did they eye blink? So you can kind of get individual activities and train people to think more intensely. You only need a single measure. That's plenty fine. A lot of these ones, the newer ones, will actually have multiple sensors across the front, just to allow an improved area or people to visualize their whole brain. Not that it actually does a lot more for your thinking areas, but it does make people feel a little happier and they're willing to keep spending money on things. So that's more of a marketing gimmick from everything I can tell than a real interest. There is a reason why you would measure the whole brain, but you don't really need to do that to train your own thinking. But hey, you got the money, who cares? So that's kind of the setup for these. And that's how I took the measurements. When we do actual measurements on this for more detailed ones, and on Thursday when we look at this, they're done by actually putting electrodes all over the head. And we kind of measure them. We start with, if you kind of take nose to the back of the head, right between the hemispheres, that's the midpoint line. And then we split the hemispheres into right and left. And then we take it at regular intervals. Straight between the ears, right, is the dead center of the brain. So that's kind of, we measure forward and back. And so then we'll just take, people will find those locations because it's easy to find the ears and to measure from where the nose is to the back of the brain. You can kind of feel on the back, you have a little nodule there. So you can find those two. So it's easy to align the caps. And then we have standard caps that have measuring positions on them. So there are a few kind of standard patterns for where the electrodes are located. And that's going to allow us to do from the ICA stuff that I talked on the most recent videos I posted last night, that allow you to kind of decompose or get these different waves. And then it will tell you when you solve the ICA problem, where were the speakers, right? Where is the activity going on inside your head? And what was the waveforms associated with that particular region. So that's why I did all that stuff on ICA and what's called blind deconvolution, because technically there is no true solution to it, but we can get it within a scale factor, and that's good enough for us. Because the amplitude doesn't matter too much to us, but the physical location and the frequency does, and ICA will give you that accurately. So it's plenty good for those. All right. Any questions?
Dr. Schubert?
Yeah.
Some question not relating to the brainwave, but more like on the pulse symmetry, the low pass filter processing.
Sure.
Yeah. So you mentioned there's you use 5 Hz corner frequency, 10 taps. We need to know your heart rate and SpO2. I think heart rate is pretty straightforward to calculate, but
yeah,
can you go through how we find SpO2?
So there are several videos that do talk about this that I've put out there. The basic idea of each of these is you've got 2 waves that are coming in. I'm not going to claim to be able to draw this perfectly. you'll see they're kind of actually whatever, a little or something like that, right? So you can get the heart rate between the peaks. If you do multiple peaks, you'll get a better average for what's on them. When you do the measurement, so this is where 0 is, and then say this is infrared and that's red. And if you watch all the videos that I've put out, I do have some ones on SpO2 calculation. We have this kind of range here. What's the min to max on the red? And I call this the AC component. And then from the 0 value up to the minimum on red is the DC component for red. And you can do the same thing for the infrared. So you'll get an AC and you'll get a DC. And if you take the AC over the DC for red, and you get the AC over the DC for the infrared, we call that ratio R. There's actually a couple different ones, like sometimes we'll take the natural log of these, but for the moment, I'm just having you do R. Right, so you can take your measurements and you can find these. If you, there's noise on here, so that's why I was saying to give it a, a low pass filter with 5 hertz as the upper, because the waves you care about are not above 5 hertz, because your heart's just not beating that fast. So if you're looking at this, you're actually, your heartbeat's really pretty close to 1 hertz. A fast heartbeat would be 2 hertz. So you're well below that 5 hertz range. So if you take a look at this, heartbeat area and you smooth it, you'll get rid of the noise spikes. So you'll get a better top and bottom value. That's really the whole reason for that smoothing of the function, is just to get the range of AC and the DC. And that's all you're reading out. And again, so you can do that across a couple of them just to get a good AC and a good DC value for each. Calculate that ratio R. And then I comment that you can plot the ratio R versus your SpO2. And if you take 100%, that happens right around a ratio R of about 0.4. And 85% saturation happens right about a ratio of 1. So you can kind of calculate this ratio, and then you can use this kind of linear curve to take from your ratio that you calculated to get a range in here. And it's pretty linear in here. It gets nonlinear outside, but it's from 100 to 85, it's pretty linear. So you don't need to add in those cubic terms and things of that sort in this range, because it's pretty flat. So basically using this and this gives it to you, but I do this in a lot more detail in one of the other videos. But this is kind of the nutshell without the full explanation of why. Does that help?
Yeah, so you mentioned some videos. I didn't know that. I just find you have a MATLAB fast ICA demo. Would that be, is that the,
You should be able to on Canvas. Let me see if I've got a.
yeah, I just find them under media gallery.
Yeah, no, if you look, so I made these modules for you, and that's why I keep mentioning the modules. Let me see if I can share my. Okay. So if this is our class thing and there's these modules here, so if you click on modules, not all the way down to media gallery, although hopefully it should be in media gallery too.
Yeah, it is.
Media gallery I find is a little bit slow. So you'll see that I've got a bunch of these different ones here. Ox Calc 2. So I mentioned Pulse Ox Calc in one of these, I think it's this video, but I'm not sure. And do some extra detail in here where I walk through it. So this is a recorded video, whatever, 14 minutes long, basically. But if you go to the modules, I kind of break them out by topic, right? So, you know, ECG, and all of these take you to wherever. So like, you know, inside here, if I went to ECG, right? You know, so this was Patrick Brands gave a MATLAB file that we had mentioned. And then I can click the next button, which goes to the next thing under this same area. And it gives you the upload for that and the basic grading rubric for it. So, you know, the modules kind of help, and I can module then once I do this, right? Pacemakers. And if you wait a sec, the videos will here. But I'm uploading and downloading, and there's a ton of other people watching things. So you'll see all those kind of pacemaker and defibrillator videos that I kind of broke out for all of you. For different aspects of this. And then I can go to next, and then there's a link to, you know, a PDF you can download of this file. And then I kind of also show the PDF here. This was my attempt at the pencast, which was not the most successful attempt early on. And so then the next one, so I click next, and this gives you a video. And you can switch here between whether you want to see my face or whether you want to see the sure, here's dominant. You might have to, but you could click play, and you can click between these. So it's, oh, sorry, it's this, the double arrow, which makes the picture big and my face small. I noticed it always defaulted to my face, so I stopped recording my face because I mean, the comfy chair and where I'm relaxing right there. So, you know, I kind of figured that was an unimportant addition, so I stopped recording those. Plus, it made these twice as big because it records the video full size. But anyway, so it's got the breakout each one, right? Blood pressure monitoring. So then there's the video for I talk about them. I had to record this one like 6 times because it kept screwing up. Got sick of it. It got shorter each time. Sorry. But you know, each one of these, right? The nears, so you can see I've broken out the videos for these. This one is the kind of class recording one, right? On hour and 15 minutes for class, and then you can see I added a little extra. I realized, oh, I didn't mention something that I wanted to, and I ran out of time, so I kind of added that one on. So you can just keep walking through each one of these, and it will break out which ones are for which. So when you get to the pulse ox, right, this is me kind of walking through and trying to run it. And then here's the pulse ox matrix, which has the data for it. And then this is a snapshot from the oscilloscope, those little orange ones that we had that of mine. I think this one is the red. I only took one picture, and this is it if you want to download it. And then I've got some ones of my build. I was just taking it with my phone. So I tried to take it from a couple directions. This is the actual circuits. I was ready to use another chip if I needed to, but it turned out I got really good measurements with a single op amp. So I was pretty happy with that. So all you see is there's a resistor here. You'll see another resistor over here. This resistor is with the button is the one to turn on the light to here. So this is that kind of tube that I put on my finger, and it's got the red and infrared on one side, and it's got the diode that comes to this amplifier on the other. So these are the pictures, and this is a download link for them. So you have them, so that you have all of my data. You have a picture of what my oscilloscope screenshot, so you can see the measurement times on it and stuff. And then you can see the circuit that I used from a couple vantage points. I wasn't sure which would turn out better. And then one of the actual measurement device had the LED hooked up to it. I thought was helpful. So that's kind of the setup for this one. But if you just keep walking through these pages, right, here's the upload for the pulse ox report. And you can go to next, which goes to the next module, which is our EEG. So this is the blind force separation. And you can see I've got my 2 videos up here. This one on kind of like a gentle introduction to PCA and ICA. This is a slideshow I actually presented to a bunch of doctors this last summer to explain this area because they use some of this, but they don't understand it. So they asked me to teach one when I was at Loma Linda for a conference. So I threw it together, and I found it helped a lot of people. So I figured I'd present it to all of you. I designed it for about a 1-hour talk, so you can see it came out pretty close to that. And then this is just, I went through and I basically did some fast ICA. Fast ICA was the original ICA algorithm that kind of took off. It didn't take forever like some of the other ones. It's about a 10 to 100 times faster than the previous ones. Hasn't really been updated since 2005, but it's good software, so it works well. So I kind of walk through how do you generate some data and process it inside of MATLAB. And then, right here, this video that we just did today is going to go right here when this is done. So these recordings that I'm making right now will probably by tomorrow morning it'll show up because WebEx is really crazy slow on doing these. So I'll upload this tomorrow. It just, for some reason, that's what it takes to generate them. And then Thursday, you can see that, we'll have another one of these. And that's why I'm going to walk through using EEG Lab. Mention, hey, if you want to download software yourself, you don't have to, but it's probably more fun. As long as you can run MATLAB, you can download this free package and you can play along with me when I'm showing you what to do. And it'll be, now that you've seen some of the brainwave stuff, you'll be more engaged, so you'll probably learn more. So I would advise it, but if you cannot download it, I understand. That video, when it's done, will go here. And that's the end of this week. And then next week, we've got the description of the entrepreneurship project. And after that, I've got the last 2 videos, which are really going to be more, I've called these ones optional, because it's really going to be a Q&A session. I need to leave you a lot of time without new material to think over to finish up your projects. And then you'll be doing your presentation. So if you look, the rest of the stuff is uploading. Upload your report, the filing document, and upload your slides and things of that sort. So the project proposal should be done a little earlier. So when I'm talking about where all these things are, you can look under the media gallery, but I would suggest walking through the modules. The modules have a lot more information in them and do have the videos linked. I'm trying to keep for you.
Is it possible that you may, I know we're running out of time. Is it possible you have a video on how to process the signal on MATLAB? Looking what we done for ECG and trying to do the low pass filter and everything. Maybe because I haven't watched the other call 2 video. Do you think that will cover most of the information I need to know?
It should cover most of it. We did, I can't, it's been a while now, but we did one where we did a finite impulse response low pass filter already. I think it was when we were still in class, but in MATLAB, it's pretty easy to do. You can make the finite impulse response. MATLAB has a command called finite impulse response 1. You can just type help space finite, and it'll give you the information on it. Basically, you pass the data to it, and you give it the break frequency, which in our case would be 5 hertz, and then you have to multiply that by what your timing is. So in our case, it would be based off of the number of samples you have. you could pass it that to give it the range of what it is. So you need FS and how big the thing is, how many total samples. But your 5 hertz is always measured relative to that area. So if you take the range of possible values for the frequencies, how far along is 5 hertz on those total number? So remember, when you take your do an FFT, you've got basically your measurement range that's on here. This is your total measurement range that's in. So you've got your, which is based off your sampling frequency. This is the midpoint. And so you've got your low frequency signals, and then it comes back to low frequency again. So it should give you this nice little symmetric curve. The range that you get off these is based on that sampling frequency, which is 1 over your time of sampling. And your sampling time is available if you read the chart. I give you what the sampling time is for this. So, you know, you have the sampling time, so you have the sampling frequency, and we want the 5 hertz, right? Which is going to be somewhere right around here. So to find that, but you're measuring it in samples, so you know the sampling frequency, right, is the total number of samples. So 5 hertz is going to be proportional, right? So, you know, 5 hertz is 1/10 of this, right? You would want 1/10 of the sampling numbers over. That's really all you're doing to put in here. So you need that times total number over FS. It's easy enough to calculate those, and we've done that one before. This will generate all of your taps, what's called the B numbers, and then you can actually use the command filter, and you pass it B, and then you pass it a 1 because we're an impulse response. That's the bottom, and then you pass it the data, if I remember correct. And that's your filtered signal, filtered F data. That's the smoothed out stuff. But you can just type help on each of these if you want some more information on how it works. If everybody has problems with it, let me know. I can do another video showing you particulars and walking you through it.
Yeah, that would be very helpful, but I'll try my best for now. Thank you.
We have done this in class though.
Yes,
So if you
yes.
look back on your notes, you know, so if it's a big help to everybody, I can do a quick processing of this. Other questions? So it's open to anything. If people have questions on, you know, the project or the lab or anything of that sort, let me know. If there are no questions, then we'll call it quits for the day. All right, well, seeing any questions popping up?
Oh, thank you.
Here. So have a good day. Watch for Thursday. If right now the link should be there. I don't know what it is, but sometimes the morning of it seems to delete the links. Please do just round if when I come in, if I notice that link is missing, be rapidly panically creating a new link, like I had to do this morning, and then I'll send out a broadcast to tell you, hey, it's there now. So sometimes it might take a couple minutes to get started if that link disappears. But right now, under WebEx, it should be there. All right. Well, thank you all for showing up. Hope things are going well. I will be around for a bit if people want to email me questions. Stay safe, everybody.